All right, welcome everybody. Think about the universe for a second. It's like this giant, super complex game, right? And to play any game, you've got to know the rules. But what if there isn't just one rule book? What if there are two? That's what we're jumping into today. The two incredible sets of rules that literally govern everything, from the phone in your hand to the farthest stars in the sky.
So let's kick things off with a question that honestly completely reshaped our world. Back in the 19th century, right, scientists thought of electricity, magnetism, and light as three totally separate things. Different forces, different rules. But someone came along and asked, what if they're not separate at all? What if just 4 lines of math could prove they're all just different sides of the same coin?
Okay, so let's dive into that first rule book. This is the one that governs the world you and I see and touch every single day. You know, the big stuff, the macroscopic world. And amazingly, it's all described by these 4 just unbelievably elegant equations put together by a genius physicist named James Clerk Maxwell. And here they are, the famous Maxwell's equations. Now I know, you see a bunch of names and laws and you might think, oh no, math homework. But don't worry about that at all. Just think of these 4 laws as, like, the source code for our entire electrical world. Seriously. Everything from why a simple compass points north to how your favorite song magically gets to your car radio. It's all in here.
Okay, let's just zoom in on one of these, because this one right here, it's pretty much the engine of our entire modern world. No joke. It's called Faraday's Law of Induction, and the idea is actually super simple, but so powerful. It just says that a changing magnetic field creates an electric field. So what does that mean in plain English? It means if you just wiggle a magnet near a coil of wire, you can literally make electricity flow. That's it. That's the core idea.
And the impact of that simple idea is just massive. I mean, every single time you flip on a light switch, you are using this exact principle. Those giant turbines you see at power plants, they're really just enormous, scaled-up versions of this. Gigantic magnets spinning near massive coils of wire, generating all the electricity that powers our homes, our cities, our lives.
But this is where Maxwell had his absolute stroke of genius. He looked at Faraday's law and saw this beautiful symmetry in how the universe works. He thought, hang on a second, if a changing magnetic field makes an electric one, shouldn't the reverse also be true? He realized that a changing electric field must also create a magnetic field. And that right there, that was the missing piece of the entire puzzle.
And that is the absolute key insight. If these two fields can create each other, they can sustain each other. An electric field wiggles, creating a magnetic field. That magnetic field wiggles, creating a new electric field a little further away. And on it goes. They could literally leapfrog through space, one creating the other, creating a wave that could travel all on its own through a total vacuum.
Okay, and this is where the story gets really, truly mind-blowing. Goosebumps level stuff. Maxwell thought, okay, if this wave exists, how fast does it go? So he decided to calculate it. He took 2 numbers, just 2 constants that scientists had figured out from doing basic experiments with electricity and magnetism, and he plugged them into his new equations for this wave.
And the number that popped out of his calculation was almost exactly 300 million meters per second, the speed of light. I mean, can you even imagine? Just from his equations about electricity and magnetism, he had predicted the exact known speed of light purely from theory. It was an absolutely earth-shattering moment. It meant that light is an electromagnetic wave. And just like that, with 4 equations, he had unified electricity, magnetism, and light into a single beautiful picture. So for a while there, it really seemed like physics was basically done, solved. But you know how it goes. As scientists started looking closer and closer, peering deep down into the world of the atom, they found something weird. Maxwell's beautiful, elegant rulebook, well, it started to break down. It just didn't work. The universe, it turns out, had a completely different set of rules for the really small stuff.
And this new reality was just plain bizarre, totally counterintuitive. In our big classical world, things are predictable. They're certain, right? You throw a baseball, you can know exactly where it is and exactly where it's going. But down in the quantum world, no way. Things are fuzzy. They're based on probability. And energy isn't a smooth ramp. It comes in these little chunky individual packets called quanta.
So this brings us to that second rule book I mentioned. To even begin to describe the strange new world, we needed a whole new way of thinking, a brand new kind of physics called quantum mechanics. And its foundation isn't built on certainty, like the old rules. It's built on probability.
And right at the very heart of quantum mechanics is this thing called the Schrödinger equation. Now, unlike Maxwell's equations, this one does not tell you where a particle is. It can't. Instead, what it gives you is something called a wave function, which is basically a recipe, a mathematical tool that tells you the probability of finding that particle right here, or over there, or somewhere else entirely.
And yeah, it gets even weirder. There's also Heisenberg's uncertainty principle. What this says is that there's a fundamental, built-in limit to what we can ever know about a particle. And this is the crucial part. It's not because our measuring tools aren't good enough, it's because the universe itself says, nope, you cannot know both the exact position and the exact momentum of a particle at the very same time. It's impossible.
This isn't a bug, it's a feature. It's a core rule in the quantum playbook. The universe, at its most fundamental level, has a built-in fuzziness. It operates on chance. The more precisely you try to pin down where a particle is, the less precisely you can possibly know where it's going. It's like trying to grab smoke. The harder you squeeze, the more it slips through your fingers. And yeah, that is a complete break from how we think the world should work.
But here's the thing, and this is probably the most important part of all this quantum weirdness, it isn't just some abstract theory for scientists in a lab. It is the absolute foundation of our modern digital world. The tiny transistors that are the heart of your computer and your smartphone, they're quantum devices. Lasers, MRIs, the atomic clocks that make your GPS work, none of it would exist if we hadn't learned to understand and use these bizarre quantum rules.
So, okay, let's put it all together. We've got these two incredibly powerful and stunningly accurate rule books for reality. And the key thing to remember is that they don't contradict each other. They each have their own domain. One perfectly describes the big world we live in, planets, people, power grids, and the other perfectly describes the invisible, tiny world of atoms and electrons.
And this really sums up our whole journey, doesn't it? On one side, you've got Maxwell's equations. They describe the big, macro world, a world of certainty and fields. And that understanding gave us the first great electronic revolution, radio, electric power, the works. Then, on the other side, you have quantum mechanics. It describes the tiny, micro world, a world of probability and little packets of energy called quanta. And that gave us the second revolution, the digital age of computers and lasers.
And that, of course, brings us to the biggest, most exciting question in all of physics today. We have these two amazing, successful rule books, but are they really separate, or do they both point to something even deeper? Is there, somewhere out there, a single unified theory, a final rulebook, a theory of everything that can describe both the big and the small in one go? Well, that question, that search, is what's happening right now at the very frontier of science. And it just reminds us that no matter how much we think we know, the universe always has another secret waiting for us.